Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about probability. Our motivation is that we're going to be studying uncertain phenomena. So we want to ask questions such as who will win the next presidential election, how much will a certain stock cost tomorrow, or when will the New York Knicks win the NBA again? In order to study this kind of phenomena, we encounter the challenge that there are different possible results that could occur, and we don't know, of course, which one is going to occur. So the strategy that we adopt is that we assign probabilities to the different possible results, depending on how likely we think they are. So in order to do this, we need to define what we mean by a probability, and that's the goal of this video. We're going to define probabilities mathematically in a formal way. But also, I hope, we're going to explain where the formal definition comes from, because at the end of the day, it essentially encodes some common sense about what we think a probability should be. And that might not be apparent if you just look at the mathematical definition. Okay, so our goal is to try to explain how the definition connects to this common sense. Okay, so then let's get to it. The prerequisites for this material are basic notions from set theory. So I just need you to know what a set is, basically something that contains some elements, and then what a union, intersection, or complement is. Okay, so the key idea is going to be that we're going to think of the uncertain phenomena that we want to study as experiments with mutually exclusive outcomes. So the outcomes cannot happen at the same time. If I roll a die, you cannot have a 1 and a 2 at the same time. That's what we mean by mutually exclusive. There's a single outcome every time we repeat the experiment. And importantly, the experiment in principle could be repeated over and over and over and over. Okay, that's what we're going to assume. Of course, it's important to emphasize that in most cases, this is just an abstraction. If we're modeling the next presidential election, we're not going to, the next presidential election is not going to happen over and over and over. It's going to happen once, and we're going to have to live with the results for the following 4 years. So we're not going to be able to repeat it over and over and over. However, thinking about it as an experiment will allow us to define probabilities and think about the uncertain and reason about the uncertain event with these probabilities, which is extremely useful. Okay, in fact, it is the cornerstone of the probabilistic modeling and statistics. Okay, so when we have an experiment, what we're going to assume again is that it has mutually exclusive outcomes. The sample space of the experiment is the set of all those possible outcomes. Okay, we usually denote it by this letter, which is big omega. All right, so in the case of where we roll a 6-sided die, the sample space or the set of all outcomes is very simple. It's just the die has 6 sides, so 1, 2, 3, 4, 5, and 6. Okay, it's the set of the numbers, the integers from 1 to 6. That's the sample space. When we try to model more complicated situations, then the sample space can also get a little bit more complicated. So let's imagine that we're rolling a die until it lands on a 6. Okay, what is the sample space there? Okay, so whenever I ask you a question like this, I would suggest that you pause the video and think a little bit about it, try to answer it. So in this case, it depends. It depends how you want to model this. You could be interested in just, how many times you need to roll the die until you get the 6. If that is the case, then your possible outcomes are positive integers, 1, 2, 3, 8, etc. However, you might also be interested in the precise sequence that happens until you roll the 6. So 2, 4, 6, or 1, 6, or 1, 3, 5, 1, 3, 1, 6. If you're interested in that, then your possible outcomes, your sample space is a little bit more complicated. It's basically sequences of numbers from 1 to 5 that end in a 6. It just depends on what you're interested in modeling. And just to illustrate further that the modeling, you often have very flexible modeling choices, is imagine that you want to model the weather tomorrow in New York City. Then there's really a lot of choices. You can model the humidity, you can model the temperature, you can model the humidity and temperature at different times, in different locations. The sample space gets extremely complicated. Let's think, just for simplicity, that you want to model the temperature at a specific time, noon, at a specific location, let's say Washington Square Park. In that case, you can represent the outcomes by a real valued number, because temperature is real valued. So we can say that in that case, the sample space is the real line. But in general, there can be very, very complicated sample spaces depending on the phenomenon that we want to model. Okay, so now that we have defined sample space and we have talked about this abstraction where we imagine that the phenomenon that we're studying is an experiment that can be repeated over and over, we're ready to give an initial overview of probability spaces, which is the mathematical framework that we're going to use to define probabilities. So again, we model the phenomenon of interest as an experiment with a sample space of mutually exclusive outcomes. And then what we do is we group those outcomes into events. These are just sets of outcomes that we find interesting, and we assign probabilities to those events. Okay, so first let's give some examples of what we mean by an event. When we're rolling the six-sided die, an event could be we roll a 1, 3, or a 5. Another possible event could be we roll a 4. Another possible event could be we roll a 1, 2, 3, 4, 5, or 6. Notice that this is actually equal to the whole sample space. Okay, the whole sample space is actually an event because it's just a set of outcomes. We say that an event happens if the outcome of the experiment is inside that set, inside that event. Okay, so now for all of these examples, which of the events happen if we roll a 4? The answer is B and C, because 4 is in B and in C it is not in A. Let's go back to our example where we roll a die until it lands on a 6. We already saw that we have these two possible options of a sample space depending on what we are interested in. Here we would model like the different sequences that happen, 1, 3, 6, 1, 4, 5, 6, and so on. Here we would just be interested in the number of rolls. And notice that here, depending on the choice that we make, the events look slightly different. So for example, the event I roll a 4, then a 5, then a 6 can be described within the first sample space. It can't really be described in the second one, okay? Here, basically, we would just have to talk about the event I rolled twice. Okay, this is just to illustrate that your choice of sample space is going to determine the kind of events that you can describe later on. So in particular, this sequence is in the first choice of sample space, but it's not in the second. Let's talk about the weather tomorrow. When we decide that the sample space is just a real number, so we're just modeling, let's say, temperature at noon in Washington Square Park. Some examples of events is the temperature is larger than 30. Or higher than 30, or exactly 35, or the temperature is just some real value. Okay, so if we measure the temperature and the temperature turns out to be 40, which of these events have occurred? And the answer is A and C, because 40 is inside A and it's inside C, but it's not in B. Okay. All right, so now that we've seen what events, some examples of events and what an event is, a probability measure is a function that maps events to a number that quantifies how likely these events are. Okay, and this number is the probability of the event. It captures, if the probability is very high, we think that the event will probably happen. If the probability is very low, we think it will probably not happen, won't happen. So here I'm using the word measure because probabilities map events which are sets to a number, and a function that maps a set to a number in mathematics is called a measure. Okay, so this might sound a little bit exotic, but that's just how we call it. Mass is another measure, area is another measure, length, and so on. Okay, so here, and this is really, really important, we're going to start with an intuitive definition of probability measure, not with a mathematical definition. We'll get to the mathematical definition later on, but in order to see why it makes sense, we need to start with an intuitive definition. Okay, the intuitive definition comes from what we want to capture with probabilities. What we want to capture is the following. If we repeat this experiment of interest many times, how many of those times would an event occur? Okay, like that number. We're going to divide it by the total repetitions. So this is the fraction of times that an event of interest occurs when we repeat the experiment over and over and over. Intuitively, that's what the probability of an event means. If a probability is 0.5, we think that if we repeat the experiment over and over and over and over, it will happen about half of the time. If the probability is 1, we think that it will happen all the time. If the probability is 0, we think that it will never happen. Okay, this is what we want to capture with probabilities. Of course, the challenge is that we're modeling often situations where the experiment is not going to be repeated over and over. Okay, so this is an abstraction, but this is what essentially what we think of, well, what we try to capture when we define probability. And we're going to use this intuitive definition to derive the properties that we think a probability space should have. Okay, so a key question here is, now we know what a probability is, a probability measure. A probability measure maps events which are sets to numbers that are probabilities. And a question is, what events should we assign probabilities to? Okay, and as we will see, when we define probability spaces formally, we're going to require that we always assign probabilities to certain events. Here, we're just going to think intuitively which events we might want to assign probabilities to. So I already mentioned that the sample space is actually an event, right? It contains all possible outcomes, so in particular, it is an event. So we should probably assign it a probability. Now, let's see what probability we should assign it according to our intuitive definition. So if the probability of the sample space, just intuitively, should be the fraction of time, that the outcome of the experiment is in that event, in the sample space, well, it turns out that all outcomes are in the sample space, right? So every time we repeat the experiment, the outcome is going to be in the sample space. So here, this fraction is just going to be equal to 1. So we should assign a probability to the sample space, and that probability should be 1. Just intuitively. Again, we haven't said anything formal yet. Okay, so imagine that we have decided to assign probabilities to two events A and B. If we do that, and we're kind of reasoning about events A and B and so on, we should probably also assign probabilities to the event that either A or B happen. Not either A or B, sorry, A or B happen. This is confusing, right? Because this is A or B, so if both happen, then A or B also happens. Sorry about that. Or to the event that both A and B happen. Okay, we should assign probabilities to the union and to the intersection of this event. In order to see what those probabilities should be like, let's start with a simple case where we have two disjoint events. Two disjoint events are events that don't share any common outcomes. This is just like disjoint sets that don't share any common elements. Okay? Okay, so imagine that we want to compute the probability that the outcome is in D1 or in D2. Okay? So intuitively, we have defined this probability to be the fraction of the outcomes when we repeat the experiment over and over and over that end up being in D1 or D2. Because the events are disjoint, the outcomes in D1 or D2 are just the sum of the outcomes in D1 plus the outcomes in D2, okay, divided by the total. But now we can just split this sum and express this probability as the sum of two fractions, the fraction of outcomes that end up being in D1 and the fraction of outcomes that end up being in D2. And of course, individually, these are just the individual probabilities of D1 and D2 by our intuitive definition. So from our intuitive definition, we see that the probability of a union of disjoint events should equal the sum of the individual probabilities. What about non-disjoint events? Okay, disjoint events don't share any common outcomes. Non-disjoint events do share some common outcomes. So we're going to apply our intuitive definition and see what happens. Okay, so just like before, we're interested in the fraction of times when we repeat the experiment over and over and over, the fraction of times that of outcomes that are in E1 or E2. Now, the number of the outcomes that are in E1 or E2 are equal to the outcomes in E1 plus the outcomes on E2, but we're double counting, right? Because if there are outcomes that are both in E1 or E2, we're counting them here and we're counting them there. So in order to not double count, we have to subtract the ones that are both in E1 and E2. Okay, and now, again, we can split this fraction into these three fractions, and this is just the probability, the fraction of outcomes that are in E1, that's the probability of E1 by our intuitive definition. This is the fraction of outcomes that are in E2, so it's the probability of E2 by our intuitive definition. And these are the outcomes that are both in E1 and E2, so it's just the probability of the intersection. Okay, so this is just derived from our intuitive definition. We think that the probability of a union should equal to the sum of the individual probabilities and subtract, and we need to subtract the probability of the intersection. So this also gives us a formula for the probability of the intersection in terms of the union. So up to now, we have decided that we should assign probabilities to the sample space and the union or intersections of events that we already have assigned probabilities to. In addition, if we assign a probability to an event A, we should probably also assign a probability to the event that A does not happen. Those are all the outcomes that are not in A. So if we think of A as a set, then this is just the complement A with like this C above. This is the probability that A does not happen. So now think for a moment, what do you think that probability should be as a function of the probability of A? And a hint here is that A and A complement are disjoint. There cannot be outcomes that are both in A and A complement just by definition. And their union is the whole sample space, right? Because each outcome in the sample space is either in A or not in A. Okay, so think about it for a moment. And the solution is that if we look at the probability of the sample space, which is equal to 1, we can split it as a sum of the probability of these two disjoint events whose union build up the sample space. So the sum of their probabilities have to add up to 1. This implies that the probability of the complement is 1 minus the probability of A. Okay, again, and this just follows automatically from our intuitive definition. Okay, so actually this is enough. Okay, we have reasoned a little bit and we've come up with some properties, well, some events that we should kind of take into account, and we have derived what probabilities we should assign to them. And now we're ready to define probability spaces mathematically. So a probability space consists of a sample space, a collection of events, this is just a set of events that we're going to assign probabilities to, and a probability measure that actually assigns those probabilities. So the collection of events is a predefined set of events that has to satisfy certain properties, and the properties are not going to be very surprising. So this collection of events has to include the sample space, because as we said, we should probably assign probabilities to the sample space. The collection of events must include the complement. So if an event is in the collection, we're going to choose this collection when we're doing modeling, okay? When we're choosing the collection of events, if we include an event, we also need to include automatically its complement. If we assign a probability to an event, we also need to assign a probability to a complement, and we already mentioned this as an intuitive thing to do. And then if we have several events that we have included in our collection, we also need to include their union. Okay? And even if this is an infinite sequence of events, we need to include the union of the infinite sequence. Okay, again, we found this quite intuitive. A collection that has these properties, a set of sets that has these properties that satisfies properties 1, 2, and 3 is called a sigma algebra. So when I started studying, probability, this would be the beginning of the course. They would tell us, oh, okay, let's start by defining sigma algebras. And I would look at this and I would be like, I don't know. I mean, why are we doing this? This seems completely arbitrary. However, if you start thinking of the intuitive definition of probability and what these events actually mean, it makes a lot of sense, right? Like you want to include your whole sample space in the sigma algebra. You want to include a complement of any event that you consider in the sigma algebra, and you also want to include unions. Okay, so quick question. According to these rules that we have defined now of what is a valid collection of events, are intersections included in the collection? So the answer is yes. Why is the answer yes? Because if we include A and B, then we're also including the complements. Oops. Sorry, my handwriting is not the best. We're also including complements. And we're also including the union of the complements. Wow. Terrible handwriting. I almost never write, so I mean, that's why. Okay, so what we also need to include the union of the complements. And now, if we take the complement of the union of the complements, which we also need to include by these rules of the sigma algebra, then this is just equal to A intersection B. So basically, this, by the way, is called the De Morgan law. Okay, you can look it up. Okay, but the point is that by the properties, so these rules that we have about what is a valid collection implies that if we consider two events, the intersection is also going to be in the collection. Okay, so just as an example, we have our rolling a six-sided die. We have that this is the sample space. So what does the collection of events look like if we want to include every individual row? Well, if we want to include every individual row, we're going to have to include all the possible unions of these guys. So that's going to be 1 and 6, 1 and 3, 1, 2, and 3, all the possible subsets of the sample space, essentially. And that's called the power set. And it has 2 to the 6. There are 2 to the 6 possible subsets. The way you can see this is that every time you build a subset, you decide whether you include each of these guys. Okay? And because there are 6 such choices, the number of possible subsets that you end up with is 2 to the 6. Okay, so there's these 64 events. So in this case, we could choose this collection of events that has these 64 possible events and assign probabilities to all of them. This is not the only possible choice. Imagine that we're just interested in whether we obtain a 2 or not. So now think, what is the smallest collection that just contains, that contains the event that a 2 was rolled? Okay, so let's get to work. Let's maybe draw the collection here. We need to include the sample space. This was the first rule. We need to include 2 because that's what we're interested in. We need to include the complement of 2. Okay, just by the rules. And we need to include the complement of the sample space. That's just the empty set, which is a really boring set. Not very interesting. And that's it. And now you might say, oh, but you need to include all possible unions and intersections. Well, the thing is that the union of this guy and this guy is just the sample space, because the sample space contains all of the possible events. Okay, just to be clear, the sample space I'm referring to 1, 2, 3, 4, 5, 6. the union of this guy, sorry, like maybe let's, the union of this guy and this guy, what is it? It's the sample space, we already have it. The intersection of this guy and this guy is the empty set, we have it. And you can check basically that we have satisfied all the rules. We have ended up with a different collection. So with this collection, we would only need to worry about assigning probabilities to these 4 sets or these 4 events. Okay, in this other one, we need to worry about assigning probabilities to 64 events. Okay, so we have already set the rules about how we need to build a collection of events when we are building a probability space. Now let's focus on the actual probability measure that maps these events to probabilities, to the numbers that we're interested in. Okay, it's a function, this probability measure, that maps events to a number between 0 and 1. By the way, the fact that this is a number between 0 and 1 captures this intuitive notion that this corresponds to some fraction of times that something will happen, right? Because a fraction of non-negative things where the numerator is at most the number of times that we're dividing, so the number of repetitions of the experiment, that's going to be a number between 0 and 1. Okay, so that is captured here. We're going to impose that the probability measure always be non-negative, and again, this is consistent with thinking of it in terms of a fraction of positive numbers. We're going to assign a probability of 1 to the sample space. This should come as no surprise. We saw that this is what that this follows immediately from our intuitive definition of probability when we apply to the sample space. And when A and B are disjoint, we're going to impose that the probability of their union has to be equal to the sum of the individual probabilities. Again, this should really come as no surprise because we have seen that this follows immediately from our intuitive interpretation of what a probability should be, what a probability measure should be. This also holds for countably infinite sequences. If you have a probability of this, I mean, this is not too important, it's just a mathematical detail, but essentially we're saying that if you take the union of a countably infinite number of events, this should also hold. If they're disjoint, then the probability of their union should be equal to the sum of the individual probabilities. If we impose these rules, we end up with what we call mathematically a measure. Other measures that can be defined in a similar way are mass, length, area, or volume, except that for this kind of measures, usually you will not have this. You will not have like a sample space that normalizes all the other measures. You will not have like a sample space. When you're defining mass, there's not like a total mass that is equal to 1. Okay, that's maybe the biggest difference between probability and these other measures. But it's sometimes useful to draw an analogy between probability and these other measures, and in particular, we can use Venn diagrams to exploit that intuition in order to and to represent events and their probability. So I'm going to just show you an example. Here we have a Venn diagram. We represent the sample space as this square that has area 1. And we represent different events through regions that enclose outcomes. So here we would imagine that the outcomes are here. These are the outcomes in A that are not in B. These are the outcomes in B that are not in A. And these are the outcomes in both A and B. So as you can see, it is very natural to visualize the intersection in this way. Okay, so here the probability of each of the events is represented by its area. So the area of the sample space is 1. The probability of A is the area of this square. The probability of B is the area of this circle. And what's neat is that because of how we have defined probability, it has to be the case that the probability of the intersection is just the area of this shape here, that is the intersection between the square and the circle, because that contains the outcomes that are both in A and in B. Okay, and Venn diagrams can be extremely useful to visualize properties of probability. I'll show you an example in a moment. In fact, right now. Okay, so we discussed, we saw that as a consequence of our intuitive definition of probability, we had that the union of non-disjoint events was equal to the sum of the probability, the probability of the union of non-disjoint events was equal to the sum of the individual probabilities, and we had to subtract the intersection. Okay, so I encourage you to derive this formally, mathematically, from the definition of probability measure, but let's use a Venn diagram to kind of prove it intuitively, and you could just make this formal by writing out the corresponding equations, but I just want to show you the the use of Venn diagrams. Okay, so here we have E1 and E2, and basically what happens here is that we want the area of this whole thing, and what we do is we separate it into the area of this part, the area of this part, and the area of this part. And what happens is that this guy is equal to, maybe I'm going to actually call this A. I should choose another color. Let me choose green. B. That's not very visible, but anyways, it will do. And okay, sorry about this. Let me choose a more reasonable color. I'll do this in black. Okay, so this, let's say that this is A, B, and C. A are all the outcomes that are in E1 and not in E2. C are all the outcomes that are in E2 and not in E1. And B are the outcomes that are both in E1 and E2. And by the rules that we have defined, the way we have defined probability measure, then this guy is equal to the sum of the disjoint events. The probabilities of the probability of the union is equal to the sum of the probabilities of the disjoint events, A, B, and C. But also, this guy is equal to the probability of A plus, the probability of this guy is equal to the probability of A plus the probability of B, right? Because the union of A and B, these are two disjoint events, they make up E1. And this guy is equal to the probability of B plus the probability of C. Again, two disjoint events, the union are E2, so that holds. And now this guy, just by definition, is the probability of B. So because of this, I mean, if you figure this out, here we have the probability of A plus B, the probability of B plus C. We have to subtract probability of B for this to hold. Again, that's the mathematical proof, but it's very easy to visualize it if you look at a Venn diagram. Okay, something else that we said is that the probability of the complement was 1 minus the probability of an event. Here again, let's draw a Venn diagram. Okay, this has a probability 1. Okay, it's a whole sample space. And now we have A that has a certain probability. And what we're interested in when we look at the probability of the complement is the probability of all the rest, right? Everything that is outside of A. So of course, if the big, in this case, rectangle, the sample space has probability 1 and the small circle has probability P of A, then the rest is going to have probability 1 minus P of A. And you can make this more formal in the same way that we made it with the intuitive definition. You have that A and A complement are disjoint events. The probability of their sum has to adapt to the probability of their union, and their union is the sample space, which has probability 1 by the definition of probability measure. Okay, so this is another important consequence of our definition of probability measure. Okay, so now let's think about how we would go about defining a valid probability measure for a concrete example. Okay, we need to assign probabilities to all the possible events in the collection. And this might seem daunting. We'll see later on that we actually never really do this. But let's work through an example. Okay, so here we're going to focus on the case where we have decided that the collection of interest in the six-sided die is the power set. Okay, all possible subsets of 1, 2, 3, 4, 5, 6. Okay? And we're going to take the following strategy. We're going to divide the sample space into the smallest possible components. These are events that are within our collection of interest, and we're going to assign probabilities to them. What do I mean by the smallest possible components? For this, I'm going to have to define a notion from set theory, which is a partition. Okay, I'm going to draw a picture. So a partition is basically, imagine, okay, this was a terrible, okay, there we go. So here we have a set, and now we want to have a partition of it. A partition is a set of subsets, okay, of this set that are all disjoint, so there cannot be elements that are in both, in two of the subsets. Okay, so it's a list of subsets which are all disjoint, so they cannot have common elements, and their union covers this set of interest. So maybe we'll choose something like this. Okay, so this would be A1, A2, A3, and A4. Okay, this is a partition of, in this case, omega. Okay, in the case of, we're talking about probability spaces, so the sample space would correspond to a set of outcomes, and this would all be events. Okay, so these 4 events, notice that because an outcome is always in one of them because they cover the sample space, one of these events always happens. Okay, when we have an outcome. And they are disjoint. Okay, so that's going to be our strategy to define the probability measure. We're going to decide on a partition, and we're going to assign probabilities to each set in the partition. Okay, so we're rolling a 6-sided die. What partition could we use here if we're interested in the collection of all possible events? A reasonable partition is just the one that consists of each event is we roll a particular value. Okay, this clearly covers, like the union of these guys is clearly equal to this, and they're all disjoint, so we're good. So now we're going to assign a probability to each of the elements in the partition. Now we need to think what conditions these numbers, so these are going to be, this theta 1 to theta 6 are going to be some probability, like the probability of theta I is the probability of rolling an I, okay, like a 1, 2, 3, 4, 5, or 6. What should these numbers, what conditions should these numbers satisfy so that we end up with a valid probability measure? So in particular, they should be non-negative, obviously. Okay, they should be non-negative. And what about their sum? So the sum of these probabilities is the sum of the probabilities of disjoint events. So that's going to be equal to the probability of their union. But their union is the whole sample space. Okay, the union is the whole sample space, and the probability of the whole sample space by definition of probability measures has to be 1. Okay, so we end up with this condition. We need 6 numbers that add up to 1. If we have 6 non-negative numbers that add up to 1, that's going to define valid probabilities on these individual events. Of course, that's not the end of the story, because we are trying to define a whole probability measure on every possible event that belongs to this collection of events. And if you remember, this collection of events has 64 possible events. It's all the possible subsets. However, the cool thing is that now, because we have chosen a partition that is very fine-grained, we can decompose the probability of any other event into a sum of, first, this is equal to the union of, the union of 2, 4, and 6. Okay, that's what this event is equal to. And these guys are all disjoint, and we have assigned individual probabilities to each of them. So now to get the probability of this event, we just sum the probabilities of its components. Okay, so in this way, we have implicitly assigned probabilities to every possible event in a way that is consistent with the definition of probability measure. Okay, and this works because the partition is fine enough. If we had chosen another partition, it might not have worked. In particular, you could think of a partition which is, for example, I roll a 2 or I don't roll a 2. This is a partition, but now how do I express this particular event in terms of this partition? I cannot. Okay, so this actually has worked out because we chose the most granular partition that we could with respect to the collection that we were interested in. If you think this has gotten very complicated suddenly, you're completely right. Defining probability measures in this way, where we take a look at what events we take into account and now we have to assign probabilities that are consistent and so on, this is a mess and we almost never do it, so don't worry. But we needed to go through this example so that you see what the logic is. Okay, later on we will define additional tools that will basically allow us to not have to worry about this kind of stuff. Okay, so let's do a recap. A probability space consists of a sample space containing all the possible outcomes of this experiment that we're using to model a certain phenomenon of interest. It contains a collection of events which are the sets of outcomes that we're going to assign a probability to. And we saw that this collection of events has to satisfy certain properties, but those properties are essentially capturing common sense. You want to include unions, you want to include the whole sample space, you want to include complements. And then you need a valid probability measure that also has its own properties that essentially follow from this intuition that this probability measure, essentially what it captures is the probability of an event is essentially the fraction of times that event is going to happen if you repeat the experiment over and over and over. Okay, the mathematical definition just captures that intuition. In order to finish the video, I would like to mention that everything we have described today is about probability theory. So probability theory provides a mathematical framework to describe uncertain events, uncertain phenomena, but it doesn't care about the connection to reality. Very soon we're going to start talking about how we estimate these probabilities from data, and that's where statistics comes in. Okay, statistics will allow us to define some of these objects and connect them. To connect the objects that we have defined through probability theory to data. Things will become a lot more messy, but they will also become more useful. It's also important to, like the interconnection between probability and statistics goes in different directions. We often use statistical techniques to build probabilistic models, which means basically objects that have a probabilistic meaning, such as probabilities, we need to estimate them from the data, so we use statistical techniques to do that. But we also go in the opposite direction. Sometimes we take a statistical technique and we use probability theory to analyze its behavior under usually some idealized assumptions. And that's basically it. Okay, so let's do a quick summary of what we have learned. We have learned the mathematical framework of probability spaces. We have, it's all based on modeling this phenomenon of interest as an experiment with a certain sample space that has mutually exclusive outcomes. We group outcomes in sets that we call events, and then we assign probabilities to those events. And that's it. Of course, I'm saying that's it, but as I said, as I was going through the example, it gets really, really complicated to build a probability space, to just actually define a probability space to model a particular phenomenon in detail so that the probabilities are consistent and so on. And the truth is that we almost never do it. Okay, this is just the mathematical foundation for a lot of, for additional objects that we're going to define. And in particular, when we define random variables, you will see that you can very quickly forget about probability spaces, but you still need to know what a probability space is so that we can actually define a random variable and start using them. All right, thank you very much.